All right, so we're going to pick up where we left off, looking here at the third law of thermodynamics. So remember, the first law of thermodynamics, energy is neither created nor destroyed. It's just converted from one form to another. And we also talked about this means that if the system loses energy, then it goes into the surroundings. So knowing that energy is neither created nor destroyed, we can transfer it from system to surroundings or vice versa. We can convert it to one form to another, but energy is conserved. Then we looked at the second law of thermodynamics, and remember the second law of thermodynamics deals with entropy, and that the entropy of the universe increases for spontaneous processes. So when we have a spontaneous process, we know the entropy of the universe. So remember, that's different from the system and the surroundings. So the change in entropy of the system plus the change in entropy of the surroundings equals the change in entropy of the universe. And so we know that if the change in entropy of the universe is a positive value, it goes up. That's a spontaneous process. And now the third law, we hinted at this in class, but the third law, the entropy of a pure crystalline substance at absolute zero is zero. All right, so let's break that down really quick. So when we look at absolute zero, remember that was 0 Kelvin. And so you see right here, that's the lowest temperature we can go is 0 Kelvin. That's one of the important things about the Kelvin scale is the lowest temperature is 0. There are no negative temperatures. At 0 Kelvin, we would say the entropy is 0, meaning, remember, entropy is related to motion. The more motion you have, the more entropy you have. So if entropy is 0, that means motion is 0. Meaning, when the temperature is 0 Kelvin, absolute 0, the molecules are no longer moving. Think back to the last video we looked at with microstates. There's no vibrational motion, no translational motion, no rotational motion. There is no motion at all, which should sort of make sense. Remember, what is temperature? Temperature is just a measure of the kinetic energy. If there is no kinetic energy, there can't be movement. If there is no movement, entropy then would be 0. And so this is the third law of thermodynamics. And so temperature, as we've said all along, plays a role in whether our processes are spontaneous or not. When we look at entropy, remember we talked about entropy being a state function, which we can do products minus reactants, just like we did for delta H. And again, you're given those values. So one thing to note is here's a table of those entropy values. Just like we solved for delta H, we can solve for delta S the same way. Delta S equals the sum of the products minus the sum of delta S of the reactants. And that formula is on your periodic table, so you can just refer back to that. The second bullet point here to make note of is entropy tends to increase with increasing molar mass. Now let's look at that for a second. So what you can see here as molecules get bigger, so maybe if we're looking here from H2 down to C6H6, right, we could look at the molar mass, and relatively we can see that as the mass goes up, the entropy goes up. Why is that? Well, what happens as the mass goes up, you're adding bigger and you're adding more molecules. So 2 or 3 molecules, 4 molecules, atoms within that one molecule. So then if you have, for example, here, C6H6, that's 6 carbons with 6 hydrogens bonded to it. That has a lot more bonds present than, let's say, something like H2O, which just has 2 bonds. The more bonds we have, the more motion you can have. So think back to microstates, think back to vibrational motion, right? Those bonds are vibrating back and forth. If you have more bonds present, you can then have more vibrational motion, and if we have more vibrational motion, we have more entropy. So just know that entropy will tend to increase with increasing molar mass. Is that true all the time? No, it's not. But in general, that's a rule of thumb we can use when looking at entropy and looking at things having more or less entropy. And so here you can see this played out with the methane, ethane, and propane. We can see, first thing to make note of, look at their entropy values. So 186, 229, 270. So entropy is going up. Notice what's happening. We can look at the mass here, which I think we can take a step back. We know that 1 carbon versus 2 carbon versus 3 carbon, right? And then these are just the hydrogens. So you could take a second if you wanted and calculate the molar mass. And you would see the molar mass is increasing from methane to ethane to propane. And because the molar mass there is increasing, the entropy is increasing. But you can see what I was talking about with the bonds. Here I have 4 bonds. Here I have 1, 2, 3, 4, 5, 6, 7 bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bonds. So 10 bonds in propane gives you 10 possibilities for vibrational motion. Where over here I only have 4 possibilities. So because we're having those more bonds, we can have more motion, and more motion means more entropy. And so here's your formula I referenced on a couple slides ago. It looks, if you go back in this PowerPoint, you go back to delta H, it's the same exact formula, except instead of using H values, we're plugging in S values. Remember, N and M are the stoichiometric coefficients from your balanced chemical equation. So you have to factor in how many of each you have from your balanced chemical equation. We would solve this the same way. So if you look back at your homework that we did a couple days ago, I believe on Monday, there was a practice problem there where you calculated delta H, and all you did, you were given the delta H standard values, you just had to do products minus reactants. Same thing that we're doing here, right? So instead of you won't be given the delta H values, but you'll be given the delta S values. So it's just a matter of doing products minus reactants and plugging those values in. And for homework today, you'll look at one and you'll practice solving using this formula. And so we'll get into our kind of last point. We'll finish this up later this week. But when we look at entropy changes in surroundings, so a couple things to look at here. So first point is heat that flows into or out of the system changes the entropy of the surroundings. And that should make sense. If we have heat going from the system and it's going into the surroundings, that means the temperature of the surroundings is going up. That means the surroundings has more energy. And if it has more energy, those molecules are moving more in the surroundings. And so then we know that the entropy of the surroundings goes up. Or vice versa. If the system is gaining heat, it came from the surroundings. So that means the surroundings lost heat, which means the temperature of the surroundings went down, which means they're moving less, they're moving slower, there's not as much energy, not as much motion, therefore not as much entropy. So just make sure you understand that. Isothermal just means same temperature. So for an isothermal process, or meaning for a process where we are not changing the temperature. And kind of like constant pressure, right? We talked about our processes occur at constant pressure because we're not changing the pressure of the environment they're in. Same thing here. They occur at constant temperature because we're not going to be changing the temperature of the environment that our process or reaction is occurring at. And so we can look at this formula, delta S of the surroundings, negative Q of the system over temperature. And really the thing to look at is negative Q of the system. That means the system is losing heat. And so we know we can look at delta S of the surroundings. And so when we look at this negative Q of the system, or it could be, the system could be gaining heat. But we know that it's going, if the system is losing heat, we know then that the heat has to go into the surroundings. And so when we look ahead, the universe we know is composed of the system and the surroundings. And that's what I kind of said earlier. So the change in entropy of the system plus the change in entropy of the surroundings will result in our overall change in entropy of the universe. And we know this, so this is the important thing to make note of. For spontaneous processes, our change in entropy will be greater than 0. So if delta S is greater than 0, then we know that this process is spontaneous. If delta S is negative, if delta S is less than 0, we know the process is not spontaneous. And so we're going to skip a couple slides so that you can look at these on your own. This is showing you how to derive a formula. So in the end, we don't really need, deriving the formula is okay. It's good to know, but due to us being online, not in class, we're not going to really take time to walk through it. We're going to skip forward here, and these are going to talk about some important points to a formula that is going to be important for us that you'll see on your periodic table, and we'll get to here in a second. So when I look here, negative T delta S of the universe is Gibbs free energy. So delta G, let's introduce one more variable, delta G. Delta G is Gibbs free energy, which we will talk about Gibbs free energy at a later date, probably tomorrow. So when delta S of the universe is positive, delta G is negative. So look here, this is the term. If this is a positive value, which means positive delta S for universe is spontaneous, then that means this overall term it's a negative times a positive, which would be a negative value. Therefore, when delta G is negative, a process is spontaneous. And this right here, this last point, I'd write this down, I'd star it, circle it, highlight it. You need to know this. So you need to know when delta S of the universe is positive, that means spontaneous. And then when delta G, if delta S is positive, that means delta G is negative. So when delta G is negative, a process is spontaneous. Again, we'll look at some practice problems down the road where we'll flesh this out. But I would say this is a big thing to make note of. Again, it goes back to this last slide where they're deriving the formula. Again, we're not going to get into deriving the formula. We just need to understand the main takeaway here is when delta G is negative, a process is spontaneous. Now, delta G is a state function, meaning I can just do products minus reactants. This formula should look very familiar. You can do, if you're given standard energies of formation, you can then do products minus reactants. And when you do products minus reactants, you can then get delta G. Just like delta H, just like delta S, you have to be given the delta G values to plug in here. And we use N and M, which are the coefficients from our balanced chemical reactions. So solving the same exact way, you would be given the numbers that you need in a table, just like we've looked at with delta H and delta S. And so this is the important formula. We'll end here, but this is the important formula. This is our formula to truly understand if a process is spontaneous or not. So delta G equals delta H minus T delta S. So there's three factors you can see in the formula, and I've talked about this before. There's three factors that control whether a process is spontaneous or not. The first is delta H. Then we also have temperature, and we also have entropy. So all three of these play a role at all times to determine whether processes are spontaneous or not. So in later days, later videos, we'll jump into this formula more. We'll dissect it. We'll use it to do calculations, and we'll explain kind of the conceptual and practical implications. But for now, we'll stop here. So don't stress too much about this formula, how to use it, when to use it. We're going to look at that in coming days.